Welcome to the Deep Dive, the show where we take the overwhelming flow of modern information, the articles, the white papers, the specialized research, and distill it into the pure, essential knowledge blueprint you need.
Today, we are tackling, I think, a foundational challenge of the modern internet.
Yeah.
It's this journey of extreme scaling. I mean, how does a small website, built by maybe one or two people on a single machine, successfully transition into a global operation?
Right, serving hundreds of millions of users.
Exactly, without collapsing into just an incoherent, expensive mess.
And that transition, it's not an accident, right? It's driven by a meticulous, evolving blueprint we call system design. Our mission today is a massive and pretty technical deep dive into the architect's toolkit.
Yeah.
We are going to look at the patterns and, crucially, the critical trade-offs that let services like Spotify or Instagram or Uber scale from, well, zero to global dominance. We're essentially reverse engineering the infrastructure that underpins the whole digital economy.
And that journey, as our sources really emphasize, it's one of continuous refinement. Success is not about finding the one right answer.
There isn't one.
There is no such thing. Successful large-scale system design is about mastering the strategy, understanding the modular components, and really internalizing the constraints and the trade-offs that you have to make at every single layer of the architecture.
And those trade-offs are everything. Cost, performance.
Resilience, yep, all of it.
Okay, let's unpack this journey. Let's start at the very beginning, because you really can't skip the fundamentals.
You can't.
We begin, logically, at the genesis. The single server setup. Just picture a bootstrap startup. One server rack, one box. Everything runs there.
Right. The web application, the database, any caching.
Yeah.
It's all just nestled together on one machine.
But it's cheap. It's simple.
And honestly, it works perfectly. For your first few dozen users, it's great.
So what does that initial request flow actually look like?
It's the classic starting point.
Yeah.
A user first accesses your domain. The domain name system, the DNS, just returns your single IP address.
The one and only.
The one and only. And the HTTP request hits that one web server. And that machine, it does everything. It authenticates the user, it runs all the business logic, it queries its own local database.
That was all the calculation.
Any calculations, yeah, before it assembles and returns, the HTML or the JSON response.
It's elegant in its simplicity, but I mean, the limitations seem terrifyingly close to the surface.
Oh, they are more than terrifying. They are existential. The immediate constraints are twofold. First, you have zero scalability.
Right.
If you suddenly get a viral moment and your user traffic increases by, say, a factor of 10, you are relying on that single machine to absorb 10 times the load.
And it just won't.
It will collapse. It'll just fall over under the combined stress of CPU, memory, and disk I/O. It'll almost always bottleneck on the disk access for the database first.
And the second limitation is the infamous single point of failure.
Correct. The core limitation is the inherent single point of failure, or SPOF, as you'll hear it called. If that one machine dies, and it will, the hard drive will fail, the power supply will go, a bug will crash the application.
Something will happen.
Something always happens. The entire website goes down completely. There is no redundancy. So any successful journey past, basic testing requires moving beyond this stage almost immediately. You have to build in resilience and capacity.
So the very first step in scaling isn't really about adding complexity. It's about separation and independence. It's about splitting the tiers.
Exactly. The first crucial architectural move is to separate the web and mobile traffic handling, which we call the web tier, from the persistent data storage, which is the data tier.
And why is that simple split so fundamental?
Because it grants us the ability to scale these two resource pools independently. Your web servers, they're often CPU intensive, right, for rendering pages and running logic. They can now grow separately from your database servers, which are usually I/O and memory intensive.
Okay, so once those tiers are separated, you are immediately forced to make the first really big architectural choice. This is the one that's going to define the rigidity or maybe the flexibility of your whole data model.
Yep.
Relational SQL versus non-relational NoSQL.
And this choice is critical. It often trips up new architects. Relational databases, so think MySQL, PostgreSQL, Oracle, they're the reliable, long-standing default.
The old guard.
The old guard, exactly. They use structured tables, rigid schemas, and most importantly, they support these powerful join operations, and they adhere to ACD properties.
Can you just quickly remind us what ACD stands for?
Sure. It's atomicity, consistency, isolation, durability. It's a set of properties that guarantee transactional integrity. So for data that is highly interlinked, like financial transactions, user accounts, complex inventory systems, SQL is almost always the superior choice because that consistency is paramount.
But then you have NoSQL, which you see everywhere in high-scale, high-velocity data platforms. So what makes that a desirable alternative, even though it sacrifices features like joins?
So NoSQL databases, which encompass several different types, key value stores like Redis or DynamoDB, document stores like MongoDB, wide column stores like Cassandra, they offer just massive horizontal scalability and performance flexibility
At a cost.
at the cost of rigid schema and that transactional integrity we just talked about. They are fantastic for storing massive volumes of simple, quickly accessible data, things like session information, user profile documents, IoT sensor readings.
So what's the takeaway here? When do you choose one over the other?
The expert consensus from the source material is pretty decisive on this. SQL should remain your default unless a relational system is demonstrably unsuitable for what you're doing.
Don't just follow the hype.
Exactly. Don't choose NoSQL simply because it's trendy. Choose it only when its specific scale or its flexibility benefits solve an immediate, acute technical problem you actually have.
Okay, so we've split the workload, we've selected our data store. Now we face the fundamental scaling choice that determines the entire trajectory of our system. Vertical versus horizontal scaling.
This is the choice. This is what separates the massive global services from the legacy systems. Vertical scaling, or scaling up, is kind of the path of least resistance at first.
You just buy a bigger box.
You just buy a bigger box, you add more power, better CPU, more RAM, faster network cards to your existing server. You're simply maximizing the performance of one individual machine. The source material notes this approach can result in some immensely powerful database servers, sometimes supporting up to 24 terabytes of RAM.
That sounds incredibly appealing for simplification. So why is horizontal scaling necessary if we can just keep buying bigger, stronger machines?
Because of the practical, economic, and physical hard limit problem. First, there's a literal ceiling. You cannot add infinite resources to one box.
Right.
Second, the cost curve is not linear. Buying a machine that is twice as powerful is often 4 or 5 times as expensive because of the specialized hardware, the licensing fees.
And the big one.
And the most critical reason, you never eliminate the single point of failure. If that one incredibly expensive, powerful machine goes down, your entire system halts. And the recovery time is often long and complex. You're completely dependent on expensive proprietary hardware and vendor lock-in, which means the only real path for a resilient, serious, large-scale application is the opposite direction.
Absolutely. Horizontal scaling, or scaling out, is the definitive choice. This means adding more commodity servers or virtual machines. You take your workload and you distribute it across a farm of many identical, inexpensive boxes.
And that's the only way to get to massive scale.
It's the only viable strategy for true large-scale applications. It inherently supports built-in redundancy. If one server fails, a load balancer just directs traffic to the others immediately. And it allows for near limitless distribution of workload. You can scale dynamically and cheaply, just adding a server only when you need the capacity. Okay, so we've committed to horizontal scaling. We now have, say, 10 web servers and 3 database servers. But this creates a coordination problem. How do we ensure a user request goes to a server that's actually available? And how do we make sure those servers share the load equally?
This is the exact job description of the load balancer, or the LB.
Yeah.
It is the traffic cop, and it sits directly in front of your web tier. Its job is efficiency.
Just directing traffic.
Just directing traffic. Distributing incoming requests across that cluster of available servers to improve the overall responsiveness and availability. They often use various algorithms like round robin.
Which is just going one by one down the list.
Yep, just rotating through the servers. Or something a little smarter like least connection, which sends traffic to the server that's currently handling the fewest active connections.
So if the load balancer is routing all this traffic, it has to know the true status of those servers constantly. How does it handle health checks and, maybe more importantly, how do we prevent the load balancer itself from becoming another SPOF?
The health check mechanism is critical. You're right. The LB is constantly pinging the servers with specific requests. If a server fails that check, maybe it's taking too long to respond, or its internal error rate threshold is exceeded, the LB automatically and almost instantly removes it from the pool.
So no more traffic goes to the dead server.
Exactly. Traffic stops flowing to that failed machine. And to mitigate the LB itself being a SPOF, you have to use a redundant setup. typically a primary or active load balancer that's monitored by a secondary passive one.
And they just watch each other.
Yeah, via a simple heartbeat mechanism. If the primary's heartbeat stops, the secondary takes over the primary's IP address immediately.
Okay, let's move to the data layer. Once we separate the database, we also need redundancy there, especially since, as we established, most user applications are really read-heavy.
Yes, and that's where master-slave database replication comes in to structure the data flow. It's the classic, simple approach for improving read performance.
How does it work?
The master database handles all the right operations, every update, every insert. This ensures data integrity and consistency for updates. The slave databases are essentially read-only copies of the master, and they handle the vast majority of read operations.
And because systems read way more than they write.
Exactly. A typical system might read 10, maybe 100 times more often than it writes, so this distribution dramatically improves system performance and capacity.
Now, if failure inevitably strikes this replicated system, what are the nuances of that failover process?
Okay, so if a slave goes offline, it's mostly manageable. The read operations are just redirected to the master or to other healthy slaves. And a new slave is provisioned, often automatically, to replace the failed one.
But the real headache is when the master goes down.
That's the real architecture headache, yes. This is a complex event. In this scenario, one of the slaves must be promoted to be the new master. This is called failover, and it is not instantaneous.
Why is promoting a master so much more difficult than just replacing a slave?
It comes down to the risk of data loss or inconsistency. The promoted slaves might not have been fully synchronized with the master at the exact moment the master failed.
So it might be missing the last few transactions?
It might be. The promotion process involves running complex consensus algorithms or data recovery scripts to make sure that the newly promoted master has the most up-to-date transaction log, or at least a known state that can be communicated to the application. If you manage this process poorly, you can lose recent writes, or the application might start interacting with inconsistent data, which is a disaster for financial or critical transaction systems.
You need a lot of sophisticated tooling around that.
You need sophisticated monitoring and coordination tools to handle this gracefully. Absolutely.
So load balancers ensure availability, replication handles redundancy. But neither of these inherently addresses the speed bottleneck of actually accessing persistent storage. The next critical tool, caching, is where we fundamentally buy back time.
Caching is the absolute lifeblood of performance in a highly scaled system. We noted earlier, right, that memory access takes nanoseconds, while disk access takes milliseconds. That's a huge difference.
Orders of magnitude.
Orders of magnitude. Caching moves frequently accessed data into fast, volatile memory. It positions it either near the application layer, in an in-memory cache, or in a dedicated high-speed distributed store like Redis or Memcached. You cache data that is read frequently, but modified infrequently.
What are the key architectural decisions you have to make when you're implementing a sophisticated distributed cache?
There are several management policies that are crucial. First, the data in the cache is volatile. It's lost on restart, so it can never be your primary persistent store. If you lose your cache, you just rebuild it from the database.
Okay.
Second, you need a carefully tuned expiration policy, or what's called a time to live, a TTL.
Right, how long the data lives in the cache.
Exactly. And the TTL dictates how long that data remains valid. This is the critical performance trade-off. A short TTL ensures you have fresher data, but it causes high database load because of frequent cache misses and reloads. A long TTL reduces the DB load dramatically, but you increase the risk of serving stale data.
And when a key does expire, there's a danger we call the thundering herd, or the cache stampede.
Absolutely. This is a classic problem. Imagine a popular item, say, the current price of stock is being queried 10,000 times per second.
Okay.
If the cache key for that price expires, all 10,000 of those concurrent requests suddenly hit the underlying database simultaneously. You overwhelm it, you cause a major slowdown, and that can potentially lead to cascading failures across the whole system.
So how do you mitigate that?
Sophisticated caching systems use techniques like cache warming, or they might have only one worker process that's responsible for refreshing an expired key, while all the others just wait briefly for the new value.
Beyond the local application cache, we have to talk about how media and files are handled globally. Which brings us to content delivery networks.
CDNs. Yeah, these are specialized, globally distributed systems focused entirely on speeding up the delivery of static assets. So your JavaScript files, CSS files, images, videos, large documents.
And the performance gain is huge.
It's enormous because the content is served from a geographically distributed server, the edge server, that's closest to the user. This minimizes the physical distance the data has to travel.
Walk us through that optimization workflow. How does the CDN save us from fetching an image from our main server in, say, New York, when the user is sitting in Sydney?
Okay, so when a user requests a static asset via a CDN-provided URL, the request is first routed by something called GeoDNS to the nearest CDN edge server.
The one in Sydney.
The one in Sydney, hopefully. That edge server checks its cache first. If it has the file, that's a cache hit. It serves it immediately, often in single-digit milliseconds. If it's a cache miss, the edge server then requests the file from the origin server.
Which is our main web server back in New York.
Or a reliable cloud storage bucket, like Amazon S3. The origin returns the file along with some crucial HTTP header information, specifically the cache control header, which contains the TTL. This header tells the CDN precisely how long it can hold on to that file before it has to consider it stale and re-request it.
But sometimes we need to change an image, we fix a logo or update a script, and we need the CDN to update it right now, even if the TTL is set for a week. We need explicit file invalidation.
Correct. You have two primary methods for fast invalidation. The first is just using the APIs provided by the CDN vendor to explicitly purge the CDN object immediately across all edge locations. This is effective, but it can take a few minutes to propagate globally.
And the other way.
The more elegant and often preferred method is using object versioning. You just change the URL. You add a new parameter or a path element. So you change image.pne to image.pne.weekly in v2, or maybe images v2 image.png.
And because the URL is different, the CDN sees it as a completely new file.
Exactly. The CDN treats the full, unique URL as the key. So the new version looks like a brand new request. It forces a fresh fetch from the origin, and it bypasses the old cached version entirely.
Okay, so now let's loop back to the web tier and address a core scaling pain point we introduced by choosing horizontal scaling. If our servers have to remember user information, we immediately derail the scale we just built. We have to enforce this shift from stateful to stateless services.
This distinction is a non-negotiable architectural decision for massive scale. A stateful server remembers client data, the state, from one request to the next.
So it knows who you are.
It knows who you are. And this requires the load balancer to use what are called sticky sessions, routing every subsequent request from, say, user A back to the exact same server 1. This means server 1 holds unique session data that no other server has.
And the scaling implications of that are disastrous.
They are. I mean, if server 1 fails, that user is logged out. Or worse, their session data is just lost until the server recovers. But more importantly, it cripples auto-scaling. You can't dynamically add new servers to meet sudden demand, because the new servers won't have the session data needed for existing users. You can't remove underutilized servers either, because you risk terminating active user sessions.
So the stateless solution removes that constraint entirely by externalizing that session state.
Precisely. The core principle of stateless architecture is that the session data, whether it's a shopping cart, a session ID, temporary preferences, it gets moved out of the web servers and into a shared, persistent, and highly available external store.
Like Redis or something.
Typically a fast distributed cache like Redis, or sometimes a dedicated database.
Yeah.
The web servers themselves are now just simple processing units that don't care which user they serve.
And what's the result of this critical shift?
The web tier becomes dramatically simpler, more robust, and elastic. Requests can now hit any server in the cluster. This allows for immediate automated scaling. If load increases, the system adds a new server instantly. It connects to the shared session store, and it's ready to serve any request.
And if load decreases?
Servers can be safely terminated without losing any user state. The web tier becomes fungible. They're all just interchangeable workers. This is the absolute prerequisite for modern cloud elasticity.
Okay, so as our system grows into the millions, our data no longer fits easily on a single master database or even a few replicas. We have to distribute data across potentially hundreds of machines, and that requires a kind of sophisticated data discipline that prevents us from falling into chaos.
It does.
Let's start with a genius concept that prevents catastrophic failure: consistent hashing.
Consistent hashing addresses this fundamental vulnerability of simple data distribution methods. If you have n servers, the simplest way to figure out where a data key should live is to use the modulo function. Server index is key%.
It's fast, it's simple.
It's a fast, simple way to ensure an even distribution.
But what goes catastrophically wrong with that simple modulo approach when we hit serious scale and need to add or remove servers dynamically?
you trigger the rehashing nightmare. It's a classic problem.
Mhm.
If you add or remove just one server, the value of n changes. Let's say it goes from 10 to 11.
Right.
Because the modular divisor changes, nearly all of your existing keys will remap to a different server index. This means adding or removing one machine causes a stampede of cache misses and incorrect database lookups, forcing every client and server to recalculate where their data is supposed to be.
It's a system-wide meltdown.
It's a system-wide meltdown.
So consistent hashing fundamentally changes the relationship between the key and the server pool to avoid this dependency on the total number of servers, on n.
Exactly. It achieves this resilience by introducing the conceptual hash ring. First, both the keys, so the data identifiers, and the servers themselves are mapped onto this large conceptual circular hash space. Usually it spans something like 2 positions.
Okay, so it's a giant circle.
A giant circle.
Yeah.
When you need to store a key, you move clockwise from the key's position on the ring until you hit the first server location. That server stores the key.
And the genius of the resilience is that it localizes the impact of any change.
Precisely. The definition of consistent hashing is that when the size of the server pool changes, only a small localized fraction of keys needs remapping. Specifically, it's about narrow keys, where k is the number of keys and n is the number of servers.
So if you add a new server,
It only takes responsibility for the keys located immediately counterclockwise to it on the ring. The rest of the ring is completely unaffected. If a server fails, the adjacent server clockwise simply picks up the slack for the keys previously mapped to that failed server. This small, localized impact allows enormous systems like Dynamo, Cassandra, and many caching solutions to scale dynamically without the chaos of a full rehash.
consistent hashing solves how we partition. The next concept, the CIP theorem, dictates the unavoidable trade-offs once that data is partitioned. This is arguably the most famous and maybe the most challenging constraint in distributed computing.
The CAP theorem, proposed by Eric Brewer, is fundamental. It states that it is impossible for a distributed system to simultaneously provide more than 2 of these 3 guarantees.
What are the 3?
Okay, they are. Consistency C, which means all nodes see the same data at the same time. Availability A, meaning every request receives a response, success or failure without exception. And partition tolerance P, which is that the system continues to operate despite arbitrary network failures or partitions.
And the choice is almost always forced upon us. Why can't we avoid partition tolerance?
Because in any modern large-scale distributed system, especially one spread across different geographical data centers, network failure is a certainty. It's not an if, it's a when. Partitions will happen. Therefore, P, partition tolerance, is mandatory. It's not really a choice.
So that forces us into a binary choice between C and A.
That's the trade-off. You can have CP or you can have AP.
Let's contrast those choices with some real-world examples. What does a CP system prioritize versus an AP system?
A CP system prioritizes consistency. So think of high-integrity systems like financial ledgers or medical record systems. If a network partition occurs and the system cannot confirm that every single node has the most up-to-date transaction,
It stops.
it chooses to block or reject the right operation. It returns an error. It sacrifices availability to ensure that data is never, ever inconsistent.
And what about the vast majority of consumer-facing internet services?
They are AP systems. Yeah. They prioritize availability. Think of an e-commerce site showing product reviews or a social media feed. If a network partition happens, the system keeps accepting reads and writes. It accepts the risk that it might temporarily return stale data, knowing the writes will be synced up later when the network partition resolves.
This is what we call eventual consistency.
This is the reality for highly scalable systems. They operate under the model of eventual consistency. Updates eventually propagate, but that instantaneous consistency across all nodes is sacrificed for speed and availability.
We can even tune this level of consistency using something called NWR quorums, right?
Yes.
Defining exactly how strongly we demand that nodes agree.
Yes, this is where the theory becomes practical tuning. NWR quorums allow you to precisely define the required consistency level. N is the total number of replicas, or nodes.
Okay.
W is the number of replicas that must confirm a write operation before the client receives success. And R is the number of replicas that must respond to a read operation before the system considers the data valid.
And the rule is what?
The critical rule is that strong consistency is guaranteed only as the number of nodes required for a write and a read, so $ plus R grass, is strictly greater than the total number of replicas, no $.
So if we have, say, 155 replicas, and we set W33 and 1 over 3 dollars and 72133, then 1 plus R is 6, which is greater than 5. We get strong consistency, but what if we're read heavy and we just want speed?
You might choose something like $1 which gives you very fast writes, since only one node needs to confirm. And maybe $$ for very fast reads. In this case, dollar plus arg is 2.2, which is less than 5. You have high availability and high speed, but your data is almost guaranteed to be eventually consistent, not instantaneously consistent. The ability to tune these parameters is what makes these distributed databases so flexible.
Since we're building these AP systems where eventual consistency reigns, we have to handle a fundamental, messy problem, data conflict. When two users in two different geographical regions modify the same replicated data at the same time, we get concurrent writes. How do systems like Dynamo resolve that inherent ambiguity?
This requires some sophisticated data versioning. The system uses vector clocks, which are crucial for detecting ancestor relationships and distinguishing a sequential update from a true conflict.
So what is a vector clock?
It's a set of server version pairs that are associated with the data item. Every time a server writes to that item, it just increments its own version counter in the clock.
So if I read version D1 from server alpha, I update it to D2 and write it back, the clock advances. What happens when the system detects that D3 and D4 were created concurrently on separate servers?
The vector clock system recognizes that D3 and D4 are siblings. They don't descend from each other. They are conflicting versions. So when the next client tries to read that data item, the system returns both conflicting versions, D3 and D4, to the client.
It punts the problem to the client.
It forces the client application, the web browser or the mobile app, to resolve the dispute. The client has to implement some kind of reconciliation policy. Maybe it merges the changes, applies a timestamp rule, or just asks the user which version to keep, and then it writes back a new unified version, say D5.
Wow, that puts immense responsibility onto the front-end engineer, the application layer, doesn't it? It's a core trade-off. Offload complexity from the core data store to the client to get maximum availability.
It absolutely is. You are trading guaranteed consistency within the database for application-level responsibility, and by doing that, you achieve superior availability. The system is always on, but the application has to be smart enough to clean up the mess when two writers overlap.
That handles soft, temporary conflicts. But what about permanent data drift? Say a replica goes offline for a month and gets seriously out of sync when it comes back online. How do we ensure long-term data synchronization without just overwhelming the network?
For handling those permanent failures and ensuring long-term synchronization, a process called anti-entropy, we leverage Merkle trees or hash trees. Merkle trees are the secret sauce for efficient background data repair in systems like DynamoDB and Cassandra.
How does a Merkle tree minimize the network transfer needed to synchronize two nodes that might hold millions of keys?
Okay, so instead of comparing every key or even large blocks of keys, we just compare the hash of the data structure's root.
The very top of the tree.
The very top. If the root hashes of two replicated nodes match, we know they are perfectly in sync and we do nothing. If they don't match, we traverse the branches down to smaller and smaller chunks of the data structure. Each branch represents a specific, contained bucket of keys. We just keep traversing until we pinpoint the exact small bucket, which might contain only a tiny fraction of the total keys. That is inconsistent.
And you only sync that one small piece.
You only synchronize that specific small bucket. This dramatically reduces the amount of data transferred and the time required to achieve long-term consistency. It's an incredibly efficient way to perform data comparison at scale.
We have mastered the stateless approach and critical data distribution. But even with the fastest, most distributed servers, certain tasks like processing a huge photo upload, compiling a monthly report, or sending out 1 billion notifications, they just take a long time.
Yeah.
If the user has to wait for those tasks to finish, the entire system response time tanks. We need to decouple our system, which is where message queues enter the picture.
Message queues, or MQs, are fundamental to modern microservice architecture because they introduce necessary asynchrony. A message queue is a durable buffer, often stored in memory or on persistent disk, that sits between system components. Its primary function is decoupling.
How so?
It shifts long-running, non-essential work away from the user's critical request path.
Explain the elegant simplicity of the producer-consumer model in this context.
Sure. A service that needs work done, the producer posts a small message to the queue indicating the job requirements and immediately returns a success code to the user.
So the user gets an instant response.
An instant response. That message is durable, it won't be lost. Other services, the consumers or workers, pick up those messages asynchronously, maybe 50 milliseconds later, and they perform the heavy lifting. A classic example is post-upload processing. The web server, the producer, confirms the upload instantly. A separate worker pool, the consumers, handles the slow tasks like image resizing, format conversion, and tagging.
The genius here is really the scaling and the failure resilience.
Exactly. Decoupling makes the system immensely failure resilient. If the consumer processing workers are temporarily unavailable, the message just remains safely stored in the durable queue, ready to be picked up later. And crucially, the producer and consumer can be scaled independently.
So if you get a big backlog,
If you suddenly see massive traffic leading to a backlog of, say, 5 million photo jobs, you simply add 100 more processing workers until the queue size shrinks. The web servers remain fast, the work gets done eventually. This architecture is also essential for coordinating global operations, supporting multiple data centers where GeoDNS routes users to the nearest center, and we have to employ synchronization mechanisms across those regional queues.
okay, moving from internal processing to protecting our system from external overload. The sheer volume of traffic and bots means we have to implement strict guardrails. Let's talk about rate limiting, which is far more than just a security feature.
Rate limiting is vital for maintaining operational stability and controlling costs. Its purpose is twofold. First, preventing resource starvation caused by intentional denial of service or DOSIS attacks, or just unintentional misbehavior by bots.
Right.
And second, by controlling the number of client requests allowed in a time window, say 5 API calls per minute from one API key, you filter out excess calls, you reduce unnecessary server load, and you prevent unnecessary costs associated with paid third-party APIs that charge per request.
Our sources detail 4 famous algorithms for rate limiting, each representing a distinct trade-off. Let's start with the one best designed for handling short bursts of traffic, the token bucket.
The token bucket is widely used by major platforms like Amazon API Gateway. You imagine a metaphorical bucket with a predefined maximum capacity. That bucket constantly receives tokens at a preset fixed refill rate.
Okay.
When a request arrives, it attempts to consume one token. If tokens are available, the request goes through and the token is removed. If the bucket is empty, the request is dropped, or maybe queued depending on your implementation.
And what's its critical advantage over other methods?
It allows for bursts. If a client hasn't sent a request in a while, the bucket might be full. That means they can suddenly execute a flurry of requests back-to-back a burst as long as those tokens last. This is fantastic for user experience because it forgives short-term sudden activity. It's also simple and highly memory efficient.
Contrast that burst controller with the stabilizing effect of the leaking bucket algorithm.
The leaking bucket is the traffic smoother. It's often implemented with a FIFO, a first-in, first-out queue. Requests fill up the queue, but they're processed at a fixed, constant outflow rate, like water leaking out of a bucket. This ensures a beautifully smooth, stable flow of traffic into your system, regardless of how spiky the input is.
But the obvious weakness there is how it handles those sudden spikes.
Exactly. It punishes bursts. A sudden spike of 1,000 requests will quickly fill the queue. If the queue capacity is exceeded, subsequent requests are dropped immediately, even if the processing workers are currently idle. And furthermore, requests that arrive first but are part of a large spike can unfairly delay new, legitimate requests that arrive later but should be processed sooner.
Okay, so if absolute, precise accuracy of the limit is paramount, if we must enforce exactly 100 requests per hour, we have to look at the sliding window log.
The sliding window log is the gold standard for accuracy because it tracks the timestamp of every single request made within the window. It often stores them in a data structure like a Redis sorted set.
So when a new request comes in,
The system efficiently removes all the outdated timestamps and then just checks if the remaining log size is within the allowed limit. The limit calculation is perfect because it considers the exact spread of traffic across the entire rolling window.
but accuracy comes at a tremendous engineering and financial cost at scale, as the sources note.
It does. The memory cost is the killer. If you are tracking, say, 1 million users, each allowed 500 requests per hour, storing all those timestamps could demand around 12 gigabytes of dedicated memory,
Just for rate limiting.
just for rate-limiting logs. For a service with tens of millions of users, this becomes economically infeasible. It is highly accurate, but it's so resource-intensive, it's really a niche choice for extremely low-volume, high-value API keys.
Which leads us to the most popular compromise that balances accuracy, performance, and cost, the sliding window with counters.
This compromise is what most large services adopt. It maintains the accuracy of the sliding window idea, but without the memory cost of logging every single timestamp. Instead of one counter for the whole window, you track request counts in smaller time windows.
Like minutes instead of an hour.
Exactly. One counter for every minute within a 1-hour limit. When a request arrives at, say, the 30-minute mark, you calculate the limit by taking the count from the preceding hours counter, so the last 30 minutes, and adding a weighted percentage of the current hours counter the first 30 minutes.
How does that approximation solve the memory problem?
It's aggregation. We are aggregating 500 potential timestamps into 60 simple integer counts. The source material estimates this approach reduces the memory footprint per user from gigabytes down to a few kilobytes, maybe around 1.6 kilobytes per user, while still effectively mitigating the major weakness of the fixed window counter.
Where you could just cram all your requests at the edge of the window.
Exactly. This offers high performance and predictable costs.
As we move from abstract principles to specific components, let's look at two critical, highly specialized tools required for enormous scale. The first, unique ID generation. When a system like Twitter needs to create IDs for 10,000 new posts per second, you can't rely on simple database auto-incrementing fields.
No, they struggle with distribution and contention. You need a globally unique 64-bit ID that is also time-ordered.
What does that mean, time order?
It means that newer posts naturally get higher IDs. And this time ordering property is immensely useful for database indexing and retrieval performance. The solution often modeled is the Twitter Snowflake model, which is a famous decentralized ID generation service.
What are the components packed into that 64-bit number to guarantee uniqueness and order?
The architecture partitions the 64 bits into 4 elements. The largest chunk, typically 41 bits, is allocated to the timestamp, usually measured in milliseconds since a specific starting point, an epoch. This ensures the time ordering.
Okay.
The next chunk, perhaps 10 bits, is reserved for the machine ID or worker ID. This identifies the specific server generating the ID, which guarantees uniqueness across the cluster. And the final chunk, often 12 bits, is the sequence number, which is incremented locally on that machine if multiple IDs are generated in the same millisecond. That handles contention and bursts.
So if the machine ID is 10 bits, that means we are capped at 1,024 unique ID generating servers, right? That's a key design constraint.
It is. The bit allocation is the trade-off. By dedicating 41 bits to time, Twitter knows they have enough runway until the year 2040 or so. By dedicating 10 bits to the machine, they limit their internal architecture to 1,024 nodes, which is plenty for most systems. The result is a unique, time-ordered, distributed ID that doesn't require communication with a single central database, a massive win for performance.
Now let's look at the efficiency of a massive distributed key value store. How do we make sure a read request is as fast as possible when the data we need might be sitting on disk, maybe across 1,000 different SS-stable sorted string tables?
Disk seeks are the great enemy of latency. They're so slow. When data is persisted in these disk files, these SS tables, in a distributed key value store, retrieving a key requires knowing exactly which file might contain it. Avoiding unnecessary disk I/O is critical, so we use Bloom filters to solve this optimization problem in the read path.
What exactly is a Bloom filter and what promise does it make to the system?
A Bloom filter is a highly space-efficient, probabilistic data structure that's implemented entirely in memory. It tells you two things very quickly. It can tell you, this key is definitely not in this specific SS stable.
A guaranteed no.
A guaranteed negative result,
Okay.
and the system can skip reading that disk file. Or it can tell you, this key might be in this specific S stable. This is the probabilistic part. It sometimes gives a false positive.
Meaning it says the key might be there when it actually isn't?
Right.
So we tolerate false positives because the cost of a false positive one unnecessary disk read is dramatically lower than the cost of a false negative, which would be missed data.
Precisely. By quickly querying the Bloom filter in memory, the system avoids reading potentially dozens of SS tables from disk that definitely won't contain the key. This dramatically speeds up the read operation, especially in databases built on LSM or log structure merge trees where data is spread across many layers of files.
We've spent this entire deep dive building this complex, multi-data center, highly distributed architecture. But once you launch, the game changes entirely. You move from construction to maintenance, and the complexity you've built demands one final necessity: operational excellence and the need for observability.
Yeah, when you're on one server, you could just SSH in and run a top command to see what was going on.
Right.
When you have hundreds of stateless machines, thousands of queue jobs, and dozens of data replicas, you need dedicated tools for observability. Scaling inherently requires rigorous monitoring, detailed metrics collection, and advanced automation support.
What kind of metrics hierarchy do we need to track across such a decentralized system?
We need visibility at 3 aggregated levels. First, Host-level metrics, so CPU
Mhm.
utilization, memory consumption, network I/O to see if individual servers are bottlenecking. Second, aggregated tier metrics, like database query latency, cache hit rate, queue depth, error rates,
Hmm.
to see the overall health of a functional component.
And the third.
Third, and most crucially, key business metrics. Daily active users, conversion rates, time to first byte. You have to ensure the system is actually serving the business goals and maintaining a good user experience. Without this observability, failure becomes inevitable and unrecoverable.
And finally, automation, which used to be optional, becomes absolutely mandatory to manage this immense complexity.
Absolutely. Continuous integration, or CI, and automated deployment, CD, are vital. When you have dozens of microservices deployed across multiple geographical data centers, you cannot rely on manual processes. Infrastructure as code, or IAC, ensures that servers are spun up and configured identically.
It's the only way to stay consistent.
Automation keeps the entire complex system consistent, it enables developers to work productively by pushing updates quickly, and it ensures that when a new server needs to be spun up due to load, the system can self-correct without any human intervention. That resilience is built on code, not on human diligence.
Wow. That was a thorough exploration of the architect's blueprint. We started with a system that could serve a few dozen users, and we ended up with a blueprint that handles billions of requests.
It's a long journey.
We discovered that the only viable path to millions of users involves horizontal scaling, adopting the stateless philosophy, decoupling long-running work with durable message queues, and introducing strict data discipline through things like consistent hashing and vector clocks.
If there is one conceptual takeaway to ground all this technical knowledge, it is the importance of choosing your architectural battles. You have to understand and accept the trade-offs. The core of scalable system design is this constant balancing act. Time versus space, cost versus performance, and the unavoidable constraint of consistency versus availability, C versus A.
And here's where it gets really interesting, connecting back to the fundamental physics mentioned in our sources. The latency numbers every programmer has to internalize. We know now that retrieving data from local memory takes 100 nanoseconds. Reading from a local SSD disk takes maybe a few milliseconds. But sending data across the continent, say from California to Virginia, takes a minimum of 60 to 80 milliseconds round trip.
And that time delay is immutable. It's caused by the fundamental constraint that light itself takes time to travel between those geographically distributed nodes.
So if you're building a consumer-facing application where the user expects an immediate response, a feed refresh, a comment, a photo upload status, you cannot afford to wait 160 milliseconds for every single global node to agree on the data's absolute instantaneous consistency.
You just can't. The user will think your app is broken.
Which means that for almost every major consumer-facing application today, the speed of light, the sheer physical time delay between data centers, forces us to prioritize availability over strict, instantaneous consistency. The user gets a response now, even if that data might be eventually consistent a moment later.
The trade-off is built into the universe, and every system designer has to concede to it.
So as you look at the systems you use every day, try to spot the components we discussed. Is that slow-loading product image coming from an edge server utilizing a CDN? When you submit a form and get an immediate processing confirmation, is that task now being handled asynchronously by a message queue?
Or, when a service is momentarily sluggish but doesn't crash, are you seeing the brilliance of consistent hashing and eventual consistency quietly keeping the architecture running beneath the surface? The infrastructure of the digital world is far more complex and elegant than it appears.
Thank you for joining us for this deep dive into the Architect's Toolkit. We'll see you next time.